Here is a number, 100,000. That is roughly how many light years across the Milky Way is. The galaxy you live in, the structure that contains your star, your solar system, every human being who has ever lived, every civilization in recorded history, every war ever fought, every love letter ever written, every photograph ever taken, the entire scope of human experience, from the first stone tool to the last satellite launched, fits inside an object 100,000 light years wide. 100,000 light years. Let's try to make that feel real for a moment before we make it feel completely irrelevant. Light moves at 300,000 kilometers per second. In 1 second, it crosses a distance roughly equal to 7.5 trips around the Earth. In 8 minutes, it covers the distance from the Sun to Earth. In about 4.25 years, it reaches the nearest star, Proxima Centauri, and across the Milky Way from one edge to the other, 100,000 light years. Light would need 100,000 years. Not 100,000 years of travel at the speed of a spacecraft, or a rocket, or even an airplane. 100,000 years at the speed of light, at the fastest speed that physics permits anything to move. The fastest possible thing in the universe, traveling for 100,000 years, barely makes it across our home galaxy. That number is staggering. It is genuinely incomprehensible to a human brain evolved to navigate distances of meters and kilometers. We do not have intuitions that scale to light years. We have to construct the comprehension laboriously, through analogies and comparisons, building a scaffolding of relative sizes that lets us stand on one number and reach toward the next. And here is the thing. The Milky Way, vast as it is, universe-breakingly, sanity-defyingly vast, is not the universe. It is not even close to the universe. The Milky Way is one galaxy, one of an estimated 2 trillion galaxies in the observable universe. Alone, 2 trillion galaxies, each one containing somewhere between 10 billion and 1 trillion stars, spread across a volume of space so enormous that the Milky Way's 100,000 light-year diameter, the number that broke your intuition a moment ago, is to the observable universe roughly what a single grain of sand is to a beach stretching from New York to Los Angeles. That is what this video is about. Not just the size comparison, though we will make that comparison as precisely and as viscerally as possible, but what the comparison means, what it implies about our place in the cosmos, what the scale of the universe tells us about the nature of space, the distribution of matter, the physics of cosmic structure, and the deepest questions about whether the universe we can see is all there is. By the end of this video, you will have a clear, grounded, scientifically precise understanding of how the Milky Way fits into its immediate neighborhood, how that neighborhood fits into the universe, and how the observable universe may fit into something larger still. Each step will be bigger than the last. Each step will be harder to hold in your mind. And each step will, if you follow the evidence carefully, change the way you see the sky above you at night. Let's build the scale from the ground up. Chapter 1. Learning to think in light. Years. Before we can understand the scale of the universe, we need to understand the unit of measurement, because light year is one of those terms that sounds familiar, but whose magnitude is almost never properly reckoned with. A light year is not a unit of time. It is a unit of distance. The distance that light travels in 1 year moving at 299,792 kilometers per second. In 1 year, light covers approximately 9.46 trillion kilometers. That is 9,460,000,000,000 kilometers. Roughly 63,000 times the distance from the Earth to the Sun. Let's build a scale model to feel this properly. If the Sun were shrunk to the size of a basketball, about 24 centimeters across, Earth at the same scale would be roughly 26 meters away, about the size of a small pea. The nearest star, Proxima Centauri, at the same scale, would be about 7,000 kilometers away. That is roughly the distance from London to New York. On a scale where the Sun is a basketball sitting in front of you, the nearest star is the width of the North Atlantic away. The Milky Way, on this basketball sun scale, would be approximately 8 billion kilometers across. For context, that is about the distance from the Sun to Pluto, 80 times over. To cross the Milky Way on our basketball sun scale would take you 80 trips from the Sun to Pluto. These numbers are already beyond comfortable comprehension. Let's shrink the scale further. Suppose instead that the entire solar system, from the Sun to the outer edge of the Oort cloud, the distant halo of comets at roughly 100,000 astronomical units, were shrunk to the size of a grain of sand, about 1 millimeter across. To that scale, the Milky Way would be approximately 1,000 kilometers wide, the width of France. A single galaxy, on a scale where the entire solar system is a grain of sand, is the width of a country. And still, the Milky Way is one galaxy out of 2 trillion. The other way to build intuition is to think in terms of travel times, using the fastest human-made objects as reference points. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object. It is traveling at approximately 17 kilometers per second, about 61,000 kilometers per hour. That sounds fast. It is genuinely fast by any human standard. At that speed, Voyager 1 would take about 75,000 years to reach the nearest star, and the nearest star is 4.24 light years away. To cross the Milky Way at Voyager 1's speed, approximately 1.7 billion years, longer than the Earth has had complex multicellular life. The Sun formed about 4.6 billion years ago. Life appeared on Earth about 3.8 billion years ago. Voyager 1 launched when Jimmy Carter was President of the United States, traveling continuously since then at its current speed without deviation, would not cross the Milky Way until nearly halfway through the age of the universe from now. This is what galaxy-sized means in practical terms. It means unreachable. It means incomprehensibly vast. It means that even the nearest star is beyond the range of any technology humans have yet developed, and the galaxy contains hundreds of billions of those stars. There is one more analogy worth building before we move on, because it reframes the scale problem in a way that is particularly useful for the rest of this video. Imagine compressing the entire history of the universe, 13.8 billion years, into a single calendar year. This is Carl Sagan's cosmic calendar, and it remains one of the most effective scale devices ever invented for this subject. On this calendar, the Big Bang occurs at the stroke of midnight on January 1st. Each month represents a little over 1 billion years. Each day represents about 38 million years. Each second represents roughly 437 years. Where do we fit? The Milky Way formed in late January, about 9 billion years before the present. Our solar system formed in early September. The first life on Earth appeared in late September. Complex multicellular life, the Cambrian explosion, didn't happen until the second week of December. The dinosaurs appeared on December 25th and went extinct on December 30th. Modern humans, Homo sapiens, appeared at 11:52 p.m. on December 31st. The entirety of recorded human history, from the first cities of Mesopotamia to the present day, occupies the last 10 seconds of December 31st. 10 seconds. The question this video is asking is, compared to the universe, how big is the galaxy? The answer, as we are about to see, is heartbreakingly small. Chapter 2. The Milky Way. What we actually know about our own galaxy. Most people have a vague sense of what the Milky Way looks like from the outside. A disk of stars, a central bulge, a few spiral arms. But the details of what the Milky Way actually is, and how we know what we know about it, are considerably more interesting than the standard description suggests. We have never photographed the Milky Way from outside. Every image you have ever seen labeled the Milky Way in the context of the full galaxy is either an artist's impression, a composite image, or a photograph of a different galaxy used as a stand-in. We know what the Milky Way looks like from the outside only by inference, by measuring the positions, velocities, and properties of millions of stars within it, and by comparing those measurements to the structures we observe in other spiral galaxies. The difficulty of studying the Milky Way from the inside is worth pausing on, because it illustrates a more general principle about how we learn anything about the universe. We are always working from within whatever we are trying to study. We cannot step outside the Milky Way to photograph it. We cannot step outside the universe to measure its total extent. Everything we know from the inside, reading signals that reach us from across space and time. For the Milky Way specifically, the challenge is obscuration. The disk of the galaxy, the plane of the Milky Way, is crowded with stars, gas, and dust. Visible light does not travel far through this dust before being absorbed or scattered. As a result, optical telescopes cannot see through the galactic disk to the far side of the galaxy. The galactic center itself, 26,000 light-years away, is completely invisible in optical light, hidden behind thousands of light-years of obscuring dust. It was only when astronomers began using infrared and radio telescopes, which penetrate dust far more effectively than visible light, that the structure of the inner galaxy became clear. The discovery of the Milky Way's bar, for instance, came primarily from infrared surveys. The COBE satellite in the 1990s revealed the characteristic boxy bulge in the infrared emission from the galactic center that indicates a bar structure. The precise mapping of the spiral arms required combining radio observations of hydrogen gas, which traces the spiral arms, with parallax measurements of star-forming regions using very long baseline interferometry, pinpointing the distances to regions across the galaxy with extraordinary precision. The Gaia satellite, launched by the European Space Agency in 2013, has transformed our knowledge of the Milky Way by measuring the precise positions and velocities of more than 1 billion stars with unprecedented accuracy. Gaia's data has revealed substructures in the galactic disk, ripples, warps, and streams that indicate the Milky Way's history of interactions with its satellite galaxies. The Milky Way's disk is not perfectly flat. It is warped at its outer edges, probably due to gravitational interactions with the large and small Magellanic Clouds. What we know is this: the Milky Way is a barred spiral galaxy. It has a central bar, a dense, elongated structure of stars running through the galactic center, with spiral arms extending outward from the ends of the bar. There are 4 major spiral arms: the Norma arm, the Scutum Centaurus arm, the Carina Sagittarius arm, and the Perseus arm, plus several minor arms and spurs. Our solar system sits in one of those minor structures, called the Orion Spur or Orion Arm, about 26,000 light-years from the galactic center. The disk of the Milky Way, the flat pancake of stars where most of the galaxy's stellar mass is concentrated, is about 100,000 to 120,000 light-years in diameter and roughly 1,000 light-years thick at our location. It is extremely thin relative to its width. If the Milky Way's disk were scaled to the dimensions of a standard vinyl record, the disk would be about 10 times thinner than the record's material. A galaxy is a pancake, not a sphere. The pancake shape is a consequence of angular momentum conservation, the same physics that makes a spinning pizza dough flatten out. But the visible stellar disk is not the full extent of the Milky Way. Beyond the disk, extending in all directions in a roughly spherical distribution, is the stellar halo, a sparse, diffuse population of old stars and globular clusters that extends to perhaps 130,000 light-years from the galactic center. And beyond even that is the dark matter halo, an enormous, invisible spherical structure of dark matter whose full extent is estimated to reach 500,000 to 1 million light-years from the galactic center. This is important for the size comparison. When we say the Milky Way is 100,000 light-years across, we are describing the visible stellar disk. The full gravitational extent of the Milky Way, the region of space that is gravitationally bound to and dominated by our galaxy, is 5 to 10 times larger. The Milky Way, properly measured, may be up to 1 million light-years across. The Milky Way contains somewhere between 100 billion and 400 billion stars. The precise number is uncertain because most stars are dim red dwarfs that are individually hard to detect at the distances of the far galactic disk. Current best estimates cluster around 200 to 300 billion stars. In addition to its stars, the Milky Way contains vast quantities of interstellar gas and dust, the raw material for future star formation, distributed in giant molecular clouds throughout the disk. The total mass of the Milky Way, including dark matter, is estimated at roughly 1 to 1.5 trillion solar masses. At the center of the Milky Way sits Sagittarius A star, the supermassive black hole that anchors the entire galaxy. Sagittarius A star has a mass of approximately 4 million solar masses. Its event horizon, the point of no return, inside which nothing escapes, has a radius of about 12 million kilometers, roughly 17 times the radius of the Sun. In April 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, showing the glowing ring of hot gas orbiting the dark shadow of the black hole's event horizon. That image was produced from data collected by radio telescopes spanning the entire Earth, working together as a planet-sized interferometer. The Milky Way is not static. It rotates. Our solar system, 26,000 light-years from the galactic center, is orbiting the galactic center at approximately 220 kilometers per second. At that speed, one orbit of the Milky Way takes about 225 to 250 million years. This is called the galactic year, or cosmic year. Earth has completed about 18 galactic years since it formed. Complex multicellular life on Earth has existed for roughly 2 galactic years. The entire period of human civilization, the 10,000 years since agriculture, represents about 0.00004 galactic years. Less than a rounding error in the Euclidean calendar of the galaxy. All of this, the 300 billion stars, the 4 million solar mass black hole, the 100,000 light-year disk, the trillion solar mass dark matter halo, is one galaxy. 1. Chapter 3, the local group. The Milky Way in its neighborhood. The Milky Way does not exist in isolation. It is part of a gravitationally bound collection of galaxies called the local group, a family of roughly 80 galaxies spread across a volume of space about 10 million light-years across. The local group has 2 dominant members, the Milky Way and the Andromeda Galaxy, also known as M31. Between them, the Milky Way and Andromeda account for the overwhelming majority of the local group's total stellar mass. The remaining approximately 78 members are smaller, a collection of dwarf galaxies and irregular galaxies orbiting the 2 giants. Andromeda is a spiral galaxy, similar in overall structure to the Milky Way, but larger. It contains roughly 1 trillion stars, 2 to 3 times the stellar population of the Milky Way, and its disk spans approximately 220,000 light-years, making it roughly twice the diameter of our galaxy's stellar disk. Andromeda sits approximately 2.537 million light-years from the Milky Way, which means the light we see from Andromeda tonight left that galaxy 2.537 million years ago, when our ancestors were early Homo habilis, chipping stone tools on the African savanna, before modern humans existed. Andromeda is the most distant object visible to the naked eye. On a very dark, clear night, it appears as a faint smudge in the constellation Andromeda, barely perceptible, easily missed. That faint smudge is 1 trillion stars. It is the equivalent of looking at the Milky Way from 2.5 million light-years away and seeing it as a dim blur in the sky. Andromeda is also approaching us. The Milky Way and Andromeda are gravitationally bound and are falling toward each other at approximately 110 kilometers per second. In about 4.5 billion years, the 2 galaxies will collide and eventually merge into a single, larger elliptical galaxy. This collision will not destroy either galaxy's stars. The distances between individual stars are so large that the vast majority will pass each other without any direct interaction. But it will dramatically reshape both galaxies' structures, disrupting the spiral arms and ultimately producing a diffuse, football-shaped elliptical galaxy that has been nicknamed Milkomeda by astronomers. Our solar system will probably survive the collision, though it may be ejected to a very different orbit in the merged galaxy. The Sun will still be on the main sequence at the time of the merger, still fusing hydrogen and still shining. The collision will be spectacular. The night sky will be filled with the distorted disk of Andromeda, occupying a region of sky many times larger than the full moon. But it will be slow by human standards. The merger will take billions of years to complete. The smaller members of the local group include the Large and Small Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere that are gravitationally associated with the Milky Way. The Large Magellanic Cloud, at about 160,000 light-years away, is close enough that a supernova in it, the most recent nearby supernova, SN 1987A, was visible to the naked eye in 1987. It was the closest supernova observed since Kepler's supernova in 1604. The light from SN 1987A had been traveling for 160,000 years before it reached our eyes. The Triangulum galaxy, M33, the third largest member of the local group, is a smaller spiral galaxy about 2.7 million light-years away and contains roughly 40 billion stars. Beyond the three major spirals, the rest of the local group is populated by a menagerie of dwarf galaxies, dwarf spheroidals, dwarf irregulars, ultra-faint dwarfs, some so dim and sparse that they were only identified in the past decade or two through sensitive sky surveys. There is a long-term fate to the local group that is worth understanding because it illustrates something fundamental about how gravity works on cosmic scales, and about what the universe will eventually look like. In the far future, after the Milky Way and Andromeda merge, the remaining members of the local group will continue to be pulled toward the merged galaxy. The smaller members, the Magellanic Clouds, the Triangulum galaxy, the dozens of dwarf galaxies, will eventually be absorbed into Milkomeda through tidal disruption and merging. Over tens of billions of years, the local group will consolidate into a single, massive elliptical galaxy surrounded by a sparse population of ejected stars. At the same time, and this is the crucial part, the rest of the universe will be receding. The expansion of the universe means that galaxies not gravitationally bound to the local group are moving away from us. And because of dark energy, that expansion is accelerating. In approximately 150 billion years, all galaxies beyond the local group will have receded beyond our observable horizon. They will be moving away from us faster than light can cross the expanding gap between us. They will be, in the most literal sense, gone, not destroyed, just forever unreachable and forever invisible. The night sky, 150 billion years from now, will contain no visible external galaxies. The merged local group will be an island in an otherwise empty, observable universe. Any civilization living in that far future, with no technology capable of detecting the faint relic signatures of departed galaxies, would have no way of knowing the universe had ever contained more than one galaxy. They would look at the sky and see their one galaxy surrounded by emptiness and conclude that the universe was small. They would be catastrophically wrong, but they would have no way to know it. We are, cosmically speaking, in a fortunate moment. The universe is old, enough that galaxies and large-scale structure have had time to form, but young enough that the expansion has not yet hidden all the evidence. We can still see the cosmic web. We can still observe galaxies billions of light years away. We can still read the history of the universe in the light that reaches us. In the far future, that evidence will be gone. the universe will have become unreadable. We live in the window of maximum legibility. The full extent of the local group, the roughly 10 million light-year volume it occupies, is itself staggering by the standards of human experience. To cross the local group at light speed would take 10 million years. To cross it at Voyager 1's speed would take roughly 200 billion years, 15 times the current age of the universe. And the local group is just one gravitational grouping within a much larger structure. Chapter 4. The Virgo Supercluster and the Cosmic Web. The local group is not the largest structure the Milky Way belongs to. Above the scale of galaxy groups lies galaxy clusters, enormous collections of hundreds to thousands of galaxies bound together by gravity. Above galaxy clusters lie superclusters, the largest gravitationally coherent structures in the universe. And all of it is organized into the cosmic web, a vast three-dimensional network of filaments and walls of galaxies, separated by enormous voids of near emptiness. The Milky Way is a member of the Virgo supercluster, also called the local supercluster, centered on the Virgo cluster about 53 million light-years away. The Virgo cluster itself contains more than 1,300 confirmed galaxies. Some estimates put the number at 2,000 or more, concentrated in a volume about 8 million light-years across. The Virgo cluster is the gravitational anchor of the local supercluster, pulling the local group and dozens of other galaxy groups toward it in what is called the Virgo infall. The Virgo supercluster spans roughly 110 million light-years and contains an estimated mass of 10 to the 15th power solar masses, 1,000,000 billion solar masses. It is one of approximately 10 million superclusters in the observable universe. But in 2014, a team of astronomers led by Brent Tully at the University of Hawaii redefined our cosmic address in a fundamental way. Using measurements of galaxy velocities, they mapped the gravitational flows of tens of thousands of galaxies and identified a much larger structure of which the Virgo supercluster is merely one lobe. They called this structure Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster complex spanning approximately 520 million light-years. It contains the mass of roughly 100,000 galaxies, totaling about 10 to the 17th power solar masses. The Milky Way sits near the outer edge of Laniakea, well outside the gravitational center. The center of Laniakea, the point toward which all the galaxies within it are flowing, is a region called the Great Attractor, a massive concentration of matter about 250 million light-years away, whose exact composition is still not fully mapped because it lies in the zone of avoidance, the part of the sky obscured by the disk of the Milky Way itself. The discovery of the Great Attractor has a history worth knowing. In the 1970s and 1980s, astronomers began noticing that the Milky Way and its neighboring galaxies were moving in a direction inconsistent with the Hubble flow, the smooth expansion of the universe. There was a systematic deviation, a peculiar velocity of about 600 kilometers per second, pointing toward a specific region of the sky. Something was pulling us, and all the galaxies around us, toward a massive, unseen concentration of matter. That concentration came to be called the Great Attractor. The difficulty was that the Great Attractor sits almost exactly behind the plane of the Milky Way's disk, in the zone of avoidance. Optical telescopes looking in that direction see only the crowded, dust-obscured foreground of our own galaxy. X-ray and radio telescopes, which penetrate the dust more effectively, have revealed that the Great Attractor coincides with a massive supercluster called the Norma cluster, a rich, dense cluster of galaxies at a distance of about 220 million light-years. But subsequent observations have shown that the Norma cluster is itself just part of a larger structure, the Shapley supercluster, lying further beyond it, and that the gravitational flow on scales larger than Laniakea is even more complex, involving multiple massive attractors whose relative contributions to the overall peculiar velocity field are still being disentangled. The velocity flow measurements that Tully's team used to define Laniakea in 2014 come from surveys of galaxy redshifts. A galaxy moving toward us, or more slowly away from us, than pure Hubble expansion would predict, has a component of its velocity that points toward a mass concentration. By mapping these departures from pure Hubble flow across tens of thousands of galaxies, the team identified the boundaries of the gravitational basin in which the Milky Way sits, the region of space that is, in a dynamical sense, our cosmic home. To put Laniakea in perspective, the Milky Way is roughly 100,000 light-years across. Laniakea is 520 million light-years across. Laniakea is approximately 5,000 times wider than the Milky Way. If the Milky Way were a marble, Laniakea would be about 5 kilometers across. And yet, Laniakea is not a particularly special structure in the universe. It is one of many comparable supercluster complexes. Its nearest peer, the Perseus-Pisces supercluster, spans a similar scale in another direction. The Shapley supercluster, one of the most massive concentrations of galaxies known, contains 76,000 galaxies in a volume about 650 million light-years across, and sits roughly 650 million light-years from the Milky Way. All of these structures, the local group, the Virgo supercluster, Laniakea, the adjacent supercluster complexes, are nodes in the cosmic web. The cosmic web is the large-scale structure of the universe, the arrangement of matter on scales of hundreds of millions to billions of light-years. It consists of filaments, thread-like concentrations of galaxies, and dark matter stretching across hundreds of millions of light-years, and nodes where filaments intersect, forming the densest galaxy clusters. Between the filaments are voids, enormous, nearly empty regions of space, typically 100 to 500 million light-years across, containing very few galaxies. The cosmic web is not random. It is the direct consequence of the pattern of quantum fluctuations in the very early universe, amplified by gravity over 13.8 billion years. Those tiny variations in density, temperature fluctuations of about 1 part in 100,000 in the cosmic microwave background, are the seeds from which all cosmic structure grew. Where the density was slightly higher, gravity pulled in more matter. The dense regions grew denser. The underdense regions grew emptier. Over billions of years, the result was the web of filaments and voids we observe today. The void structure of the cosmic web deserves particular attention because it exposes something deeply counterintuitive about the universe's large-scale composition. The vast majority of the universe's volume, roughly 80% of it, is occupied by voids, regions of space that are nearly empty of galaxies, dark matter, and visible structure. The Bode's void, one of the largest known, is approximately 330 million light-years in diameter. If the entire Milky Way were placed at its center, the nearest galaxy outside the void would be 165 million light-years away, farther than the current distance to the Virgo cluster. What exists inside the great voids? Almost nothing. A handful of galaxies, typically filamentary and underdeveloped, scattered through an essentially empty volume of space. Oh, civilization living in a galaxy deep inside a cosmic void would, when they built their first telescopes, see remarkably little. The night sky would be no darker in terms of the number of stars visible in their own galaxy, but the intergalactic view would reveal almost no other galaxies, no visible clusters or superclusters, no nearby cosmic web structure. Their observable universe would look, at large scales, almost entirely empty. They might reasonably, for a long time, conclude that their galaxy was alone. The cosmic web, with its dense filaments and bustling clusters, would only emerge from their telescopes at very great distances, a pattern invisible from inside a void. We are fortunate. The Milky Way sits in a modest overdensity, a filament node in the local group, itself part of Laniakea. Our view of the cosmic web is not the best possible. We are not inside a rich cluster with thousands of galaxies in our immediate neighborhood, but it is vastly richer than the view from inside a void. Mapping the cosmic web has been one of the great achievements of observational cosmology in the past 4 decades. The CFA Redshift survey of the 1980s revealed the first large-scale structures. The Great Wall, a sheet of galaxies 500 million light-years long, discovered by Margaret Geller and John Huchra. The Sloan Digital Sky Survey, begun in 2000, mapped the positions of more than 1 million galaxies and revealed the cosmic web in extraordinary detail. The ongoing DESI survey aims to map 40 million galaxies, producing the most detailed 3-dimensional map of the cosmic web ever made. Chapter 5. The Observable Universe, the Edge of What We Can See. We have been building up the scale steadily. From the Milky Way's 100,000 light-years, to the local group's 10 million, to the Virgo supercluster's 110 million, to Laniakea's 520 million, to the scale of the cosmic web at hundreds of millions, to billions of light-years. Each step bigger by roughly an order of magnitude. Now we reach the largest scale we can directly observe, the observable universe. The observable universe is defined by a simple physical principle. Light travels at a finite speed. The universe has a finite age, 13.8 billion years. Therefore, we can only see objects whose light has had time to reach us since the universe began. Objects beyond a certain distance are, in principle, unobservable. Their light has not had time to reach us yet, and crucially, because the universe is expanding, light from very distant objects may never reach us, no matter how long we wait. Before we get to numbers, it's worth understanding the primary tool astronomers use to measure cosmic distances: redshift. When a source of light is moving away from you, the wavelengths of its light are stretched, shifted toward the red end of the spectrum. This is the Doppler effect, the same physics that makes a passing ambulance's siren drop in pitch as it moves away. In cosmology, the redshift of distant galaxies is not caused by their individual motion through space, but by the expansion of space itself. The wavelengths of light are stretched as they travel through an expanding universe, with the degree of stretching proportional to how much the universe has expanded during the photon's journey. Astronomers denote redshift with the letter Z. A galaxy at Z equals 0.1 has its light wavelengths stretched by 10%. It is relatively nearby, a few 100 million light-years away. A galaxy at Z equals 1 has its light stretched by a factor of 2. It is billions of light-years away, and we are seeing it as it existed billions of years ago. The most distant galaxies individually detected have redshifts above Z equals 13, placing them in the first few 100 million years of cosmic history. The cosmic microwave background itself has a redshift of Z approximately 1,100. The light has been stretched to over 1,000 times its original wavelength on its journey from the early universe to our detectors. Redshift is therefore simultaneously a distance indicator and a time machine. A galaxy at high redshift is not just far away, it is young. We see it as it existed billions of years ago, when the universe itself was younger, denser, and more chaotic. The deepest telescopic images are not just maps of space, they are maps of time. The naive estimate of the observable universe's radius would be 13.8 billion light-years. The distance light can travel in the age of the universe. But this estimate is wrong for a reason that is both elegant and disorienting. The universe has been expanding throughout its history. When a photon was emitted from a distant galaxy, that galaxy was much closer to us than it is today. By the time the photon reaches us, the galaxy has been carried farther away by the expansion of space. The photon's journey is longer than it would be in a static universe, and the galaxy's current distance is greater than the light travel distance to it. The correct calculation, accounting for the expansion history of the universe, gives an observable universe with a radius of approximately 46 billion light-years. The observable universe's diameter is therefore roughly 93 billion light-years. The co-moving volume of the observable universe, the volume of space we can in principle observe, is approximately 4 times 10 to the 26th power cubic meters, or about 4 times 10 to the 80 power cubic centimeters. The observable universe contains an estimated 2 trillion galaxies. This number was dramatically revised upward in 2016, when a study led by Christopher Consolis used deep field images from the Hubble Space Telescope to estimate the total number of galaxies more carefully. Previous estimates had suggested around 200 billion galaxies. The 2016 study revised this to approximately 2 trillion, based on modeling of the many small distant galaxies too faint to be individually detected in current surveys. 2 trillion galaxies. If you counted 1 galaxy per second, it would take you more than 63,000 years to count them all. If every galaxy contained an average of 200 billion stars, a conservative estimate, the total number of stars in the observable universe would be roughly 4 times 10 to the 23rd power stars, 400 sextillion stars. More stars than grains of sand on every beach and desert on Earth, combined by a factor of roughly 10,000. One way to feel what 2 trillion galaxies means observationally is to look at the Hubble Ultra Deep Field. A photograph taken by the Hubble Space Telescope in 2003 and 2004 by pointing the telescope at a tiny, apparently blank region of sky in the constellation Fornax and leaving the shutter open for nearly 1 million seconds of cumulative exposure over 400 orbits. The resulting image covers an area of sky so small that you could block it with the tip of a sewing needle held at arm's length. In that needle tip of sky, the Hubble Ultra Deep Field revealed approximately 10,000 galaxies. Galaxies at all distances, in all stages of development. Spirals, ellipticals, irregular dwarfs, the blue, compact, chaotic galaxies of the early universe, the more settled, mature spirals of the recent universe, all crammed into a sliver of sky so small that it is invisible to the naked eye. If the sky contains roughly 10,000 galaxies in every needle-tip-sized patch, and the total sky covers about 170 billion such patches, then the total number of galaxies visible to a telescope like Hubble is around 200 billion in the near-term observable universe. The factor of 10 revision to 2 trillion accounts for the vast population of smaller, dimmer, more distant galaxies that Hubble cannot resolve individually. The galaxies that are there, but that blur into the background glow of the deep field images. The universe is not mostly empty in the sense of being featureless. It is full, overwhelmingly full, of galaxies, clustered and threaded and webbed across the entire observable volume, separated by voids, but never truly isolated. The observable universe's diameter of 93 billion light-years compared to the Milky Way's 100,000 light-years gives a ratio of approximately 930,000. The observable universe is roughly 1 million times wider than the Milky Way. In 3 dimensions, the volume comparison is that ratio cubed, meaning the observable universe is roughly 10 to the power of 18 times larger in volume than the Milky Way. 1 billion times larger. But here is what makes the observable universe concept both clarifying and slightly vertiginous. The observable universe is not the universe. It is a sphere around us, defined by what we can see, given the speed of light and the age of the universe. An observer in a galaxy 10 billion light-years away would have a different observable universe. A sphere centered on them, overlapping with ours, but not identical. Their sphere would contain different galaxies, different structures, potentially different cosmic neighborhoods. The totality of all observable universes, all the spheres centered on every possible observer, is larger than any single sphere, and the actual universe may be larger still. Chapter 6. Beyond what we can see, the full universe and its possible scales. The observable universe, vast as it is almost certainly not the full universe. It is a finite observable patch, defined by the speed of light and the history of expansion. A cosmic horizon beyond which we cannot see, not because there is nothing there, but because light from those regions has not yet reached us, or is being carried away by expansion faster than it can approach. The question of how large the full universe is, beyond the observable sphere, is one of the deepest and most actively debated questions in cosmology. The answer depends on the geometry and topology of the universe, and on whether the universe had a finite or infinite beginning. The best current measurements, primarily from the Planck satellite's maps of the cosmic microwave background, constrain the geometry of the universe to be very close to flat. A flat universe, in the context of general relativity, means that the large-scale geometry of space follows the rules of ordinary Euclidean geometry. Parallel lines remain parallel, the angles of a triangle sum to 180 degrees, and the volume of space grows as a simple cubic function of radius. A flat universe can be either finite or infinite. If it is infinite, the universe extends without limit in all directions, containing infinitely many galaxies, infinitely many stars, and given enough volume, infinitely many repetitions of any finite pattern, including, in principle, exact copies of our observable universe, our galaxy, our solar system, and even us. If the flat universe is finite, it must have a specific topology, a way of connecting back on itself. The most commonly discussed finite flat topology is the 3 torus, an analog of the way a two-dimensional video game screen wraps around. When you exit the right side, you reappear on the left. In a 3 torus universe, traveling far enough in any direction would bring you back to your starting point. We have searched for signatures of this topology, repeated patterns in the cosmic microwave background, identical galaxy pairs separated by a specific distance, and found none. This constrains the minimum size of a toroidal universe to be at least several times larger than the observable universe, meaning no repeats are visible within our observable sphere. The inflationary cosmology, the theory that the universe underwent an exponential expansion phase in the first tiny fraction of a second after the Big Bang, provides a natural mechanism for a universe much larger than the observable sphere. During inflation, space expanded at an exponential rate, potentially taking a small, causally connected region and expanding it to a size vastly larger than today's observable universe. Post-inflationary estimates, depending on the specific model, suggest that the full universe could be anywhere from 10 to the power of 23 times larger than the observable universe to truly infinite. Even at the most conservative estimate, 10 to the power of 23 times larger. The full universe contains approximately 2 times 10 to the power of 35 galaxies. That is 200 billion trillion galaxies. The number is so large that it ceases to have intuitive meaning and exists only as an abstract algebraic expression. The Milky Way, compared to the full universe, even at conservative estimates, is to the full universe what a single atom is to a grain of sand. Less, actually, far less. The ratio of a single hydrogen atom's diameter to the observable universe is about 10 to the power of minus 35, comparable to the ratio of the observable universe to the inflationary estimate of the full universe. In other words, if the inflationary model is right, the observable universe's relationship to the full universe is roughly the same as a single hydrogen atom's relationship to the observable universe. And the Milky Way, sitting inside the observable universe, is smaller still, by another factor of 1,000,000 in each direction. Chapter 7. What structure tells us? Reading the universe's size through its architecture. We have been discussing the universe's scale as though it were simply a question of measurement. Point a telescope, look at distant objects, count and measure. But the scale of the universe is actually encoded in its structure, and reading that structure is one of the most powerful tools cosmologists have for understanding the cosmos. The cosmic microwave background, the CMB, is the oldest light in the universe. It was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms, making the universe transparent to light for the first time. Before that moment, the universe was opaque, a hot, dense plasma through which photons could not travel freely. The photons released at the moment of recombination have been traveling ever since, redshifted by the expansion of the universe from the temperatures of a glowing plasma to the microwave wavelengths we detect today. The CMB fills the entire sky uniformly at a temperature of 2.725 Kelvin, just 2.725 degrees above absolute zero. It is the most perfect blackbody radiation ever measured, and it is extraordinarily uniform. The temperature varies by less than 1 part in 100,000 across the entire sky. But those tiny temperature variations are not noise. They are structure. The fluctuations in the CMB are the imprint of acoustic oscillations in the early universe's plasma. Sound waves, propagating through the hot, dense gas of the early cosmos, creating patterns of compression and rarefaction at scales determined by the size of the cosmic horizon at the time of recombination and by the speed of sound in the plasma. The angular scale of the largest features in the CMB, the first acoustic peak, is about 1 degree, corresponding to a physical scale at the time of recombination of roughly 300,000 light years. But here is what makes the CMB so powerful for measuring the universe's geometry. If we know the physical size of the acoustic scale at the time of recombination, which we calculate from the known physics of the plasma, and we measure the angular size of that feature in the CMB, which we observe with telescopes, we can calculate the geometry of the space through which the light has traveled to reach us. If the universe is flat, the angular size should be about 1 degree. If it is positively curved, like the surface of a sphere, the features should appear larger. If it is negatively curved, like a saddle, they should appear smaller. The measured angular scale is, within the precision of current measurements, exactly 1 degree. The universe is flat to a precision of about 0.4%. This measurement alone tells us that the full universe must be many times larger than the observable sphere, because only a universe much larger than what we can see would appear flat to this precision from any observer within it. The acoustic scale of the CMB also provides the most direct measurement of the physical scale of the universe, the Hubble constant, the rate of expansion. The Hubble constant, currently measured at approximately 67 to 73 kilometers per second per megaparsec, with an ongoing tension between different measurement methods that is one of the most active debates in modern cosmology, tells us how fast space is expanding. Every megaparsec of space, every 3.26 million light years, is growing by 67 to 73 kilometers per second. The universe is not expanding into anything. Space itself is expanding. The distance between any two galaxies that are not gravitationally bound to each other is increasing. The Hubble tension, that gap between 67 and 73, is worth dwelling on because it is not a trivial measurement uncertainty. It is a discrepancy between two of the most carefully executed programs in observational astronomy, using entirely independent methods, both of which claim precisions of a few percent. yet which disagree at a level of statistical significance that should not occur by chance. The value of 67 kilometers per second per megaparsec comes from the Planck satellite's analysis of the CMB, the oldest light in the universe, the physics of which is understood with extraordinary precision from first principles. The value of 73 kilometers per second per megaparsec comes from the distance ladder, a chain of distance measurements starting with Cepheid variable stars and Type 1a supernovae calibrated against them, extending out to cosmological distances. The James Webb Space Telescope has now confirmed the distance ladder measurements with even greater precision, ruling out the most commonly suggested systematic errors. If both measurements are correct, and both teams argue strenuously that they are, then there is something wrong with our current cosmological model. The standard model of cosmology, called lambda CDM, lambda cold dark matter, does not produce the observed tension. It predicts a universe that expands at one rate when measured via the CMB and the same rate when measured via the distance ladder. The fact that two completely different measurement approaches give systematically different answers suggests either a subtle systematic error in one or both, which decades of checking have failed to find, or new physics, something beyond the standard model that affects the expansion history of the universe. The candidates for that new physics are numerous: early dark energy, interacting dark matter, additional light particles in the early universe, a modified theory of gravity. None has yet been confirmed. The Hubble tension remains open, but its existence is itself a clue about the structure and scale of the universe. A clue that the universe's history of expansion, which determines its observable size, may be more complicated than the simplest model suggests. This expansion has a direct consequence for the size of the observable universe. The most distant objects we can observe, at a redshift of about 1,100, corresponding to the surface of last scattering of the CMB, emitted their light 13.8 billion years ago. But those objects are not 13.8 billion light-years away today. The expansion of the universe has carried them much further. Today, the objects from which the CMB photons were emitted are approximately 46 billion light-years away, the edge of the observable universe. And beyond that edge, the universe continues. We simply cannot see it. Chapter 8: Dark Matter and Dark Energy. The invisible architecture of scale. Here is something that should be mentioned whenever anyone discusses the size of the universe, and almost never is. Most of the universe is invisible. Not invisible in the sense of being too faint to see with current telescopes. Invisible in the sense of not interacting with light at all, not emitting it, not absorbing it, not scattering it. The matter and energy that make up everything we have discussed so far, the galaxies, the stars, the gas, the dust, the planets, the black holes, the cosmic web of visible structure, accounts for approximately 5% of the total energy content of the universe. 5%. The remaining 95% is divided between two things we cannot directly observe, whose fundamental nature we do not understand, and whose existence we infer entirely from their gravitational effects on the 5% we can see. The first is dark matter. It makes up approximately 27% of the universe's total energy content. It does not emit, absorb, or reflect electromagnetic radiation of any wavelength. It does not participate in the electromagnetic force at all, as far as we can tell. It interacts gravitationally. It has mass, and it responds to gravity and produces gravity. And it may interact via the weak nuclear force, but that is essentially where its participation in known physics ends. We know dark matter exists because of what it does to the things we can see. Galaxies rotate in ways that can only be explained if they contain far more mass than their visible stars and gas account for. The rotation curve of a typical spiral galaxy, the speed at which stars orbit the galactic center as a function of their distance from it, should by Newtonian gravity decline with distance beyond the disk. The same way the orbital speed of planets in the solar system declines with distance from the Sun. Instead, the rotation curves of spiral galaxies are flat. Stars at the outer edge of a galaxy orbit at roughly the same speed as stars near the center. The only explanation consistent with known physics is an extended halo of invisible mass, dark matter, surrounding the visible disk and extending far beyond it. The rotation curve problem was first identified seriously by astronomer Vera Rubin in the 1970s, working with the spectroscopist Kent Ford. They measured the Doppler shifts of stars and gas across the disk of Andromeda and found, to their initial surprise, that the outer regions were rotating just as fast as the inner ones. By Newtonian gravity, this was wrong. The outer material should have been moving more slowly. Rubin and Ford's result, replicated across dozens of galaxies by subsequent observers, was the first unambiguous observational case for dark matter, leading directly to the modern picture of galaxies as luminous cores embedded in vast invisible halos. Rubin later described the discovery as making the universe feel far stranger than anyone had suspected. Not philosophically troubling exactly, but humbling in a specific way. The visible universe, everything ever observed, measured, and theorized about through all of astronomy's history, turned out to be a minority, component of total physical reality. The bulk of a galaxy's mass is dark matter, distributed in a halo that dwarfs the luminous disk. Every star you have ever seen through a telescope or with the naked eye is part of the 5%. The Milky Way's dark matter halo is estimated to extend to between 500,000 and 1 million light-years from the galactic center. The visible stellar disk, 100,000 light-years across, sits at the core of a dark matter halo 5 to 10 times larger. When we say the Milky Way is 100,000 light-years across, we are describing the luminous tip of a much larger invisible structure. The same is true for every galaxy in the universe, for every galaxy cluster, and for the large-scale structure of the cosmic web itself. The filaments of the cosmic web are not primarily made of galaxies. They are made of dark matter, with the visible galaxies tracing the densest concentrations of that dark matter, like lights strung along an invisible scaffolding. The voids are not just empty of galaxies, they are empty of dark matter. The real skeleton of the universe is written in dark matter, and the galaxies are just the annotations. The evidence for dark matter is not limited to galactic rotation curves. The most visually compelling single piece of evidence is the Bullet Cluster, two galaxy clusters that collided roughly 150 million years ago. When galaxy clusters collide, the visible gas, which makes up most of a cluster's baryonic mass, slows down due to electromagnetic interactions and piles up between the two clusters. But the dark matter, which does not interact electromagnetically, passes straight through, like two ghosts walking through each other. Gravitational lensing measurements of the bullet cluster map the total mass distribution independently of the light, and they show two distinct mass concentrations, one for each cluster, separated from the visible gas that sits between them. The mass went one way, the light went another. Dark matter and ordinary matter separated by a collision. The frustrating thing about dark matter is how extensively we have tried to detect it directly and failed. Dozens of experiments buried deep underground to shield them from cosmic ray interference, filled with ultra-pure materials, cooled to near absolute zero to reduce thermal noise, designed to detect the faint recoil of an atomic nucleus struck by a passing dark matter particle, have run for years without a confirmed detection. The LHC at CERN has searched for dark matter production in particle collisions. Gamma-ray telescopes have searched for the photon signal that some dark matter candidates would produce when two dark matter particles annihilate each other. Nothing confirmed. This does not mean dark matter does not exist. It means either that its cross-section for interaction with ordinary matter is smaller than our most sensitive detectors can yet measure, or that its particle properties are different from what the most popular theoretical candidates, weakly interacting massive particles, or WIMPs, predict. The search continues with increasingly sensitive instruments, but the gap between the overwhelming gravitational evidence for dark matter and the complete absence of a direct detection signal is one of the central puzzles of 21st century physics. The second invisible component is dark energy. It makes up approximately 68% of the universe's total energy content, the single largest component of the cosmic energy budget, and the most mysterious. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. In 1998, two independent teams measuring the distances and redshifts of Type 1, a supernovae, discovered that distant supernovae were fainter than expected, systematically farther away than a decelerating universe would predict. The universe was not just expanding, it was expanding faster and faster over time, driven by something that behaves like a repulsive energy intrinsic to space itself. The simplest description of dark energy is the cosmological constant, the energy density of empty space, representing a fixed amount of energy per unit volume of the vacuum. As the universe expands and more vacuum comes into existence, more dark energy is created alongside it. This is what makes dark energy different from matter and radiation, which dilute as the universe expands. Dark energy maintains a constant density and therefore becomes an increasingly dominant component of the universe's energy budget as expansion continues. The cosmological, constant interpretation of dark energy, while mathematically elegant, is physically deeply puzzling. Quantum field theory predicts that the vacuum should have an energy density, that quantum fluctuations should contribute to the energy of empty space. It also predicts that this energy density should be enormous, approximately 10 to the power of 120 times larger than the observed value of the cosmological constant. This 120 order of magnitude discrepancy between the theoretical prediction and the observed value is known as the cosmological constant problem, and it is widely considered the worst prediction in the history of physics. Something is suppressing the vacuum energy by 120 decimal places, and we have no idea what. The scale implications of dark energy are profound. Dark energy is what drives the accelerating expansion that will eventually push all galaxies beyond our local group, beyond the observable horizon. It is the force, if force is even the right word for a property of space itself, that is slowly but inexorably separating the local group from everything else in the universe. The larger the universe gets, the more dark energy exists, the faster it expands, in a runaway process that will eventually leave the merged Milky Way Andromeda galaxy in an apparently empty universe. On the scales we have been discussing throughout this video, scales of billions of light years. Dark energy is the dominant factor determining the geometry, the expansion history, and the ultimate fate of everything. And we understand it barely at all. There is a more precise way to describe just how little we understand it. There are 3 possible fates for the universe depending on the nature of dark energy. If dark energy is truly a cosmological constant, a fixed energy density of empty space, then the universe expands forever, galaxies recede beyond the horizon, stars burn out, black holes slowly evaporate via Hawking radiation over incomprehensible timescales, and the universe approaches a cold, dark, maximally disordered state called the heat death. This is the current best guess trajectory. If dark energy increases in strength over time, a scenario called the Big Rip, the accelerating expansion eventually overwhelms all forces. First, galaxy clusters are torn apart by the expansion, then galaxies, then solar systems, then planets. Then, in the final moments, atoms themselves are ripped apart by the expanding fabric of space. The Big Rip, if it occurs, happens in a finite time that depends on the specific rate at which dark energy grows. Some models place it tens of billions of years in the future. The physics of what happens to matter in the final seconds of a Big Rip universe is genuinely unknown. If dark energy decreases in strength, or if the universe has a positive spatial curvature we have not yet detected, the expansion could eventually reverse, leading to a big crunch. The universe collapsing back to a hot, dense singularity, the mirror image of the Big Bang. The Big Crunch has fallen out of favor as an end-state scenario given the acceleration data, but it cannot yet be entirely excluded. The ultimate fate of the universe, and therefore the ultimate fate of everything the universe contains, including every galaxy, every star, every possible civilization, depends entirely on the nature of dark energy, which we do not understand. The universe is not made of stars and gas. It is made of dark matter and dark energy, with stars and gas as a thin, luminous glaze on a vast, invisible structure. Everything we can see, every galaxy, every star, every atom that makes up every planet and person and civilization in the observable universe, is a small fraction of a small fraction of what actually exists. Chapter 9: How the comparison actually feels. Building the final number. We have been building toward a number, a ratio, the answer to the title of this video. How big is the universe compared to our galaxy? We have the pieces. Now let's assemble them into the clearest possible picture. The Milky Way's visible stellar disk is approximately 100,000 light-years in diameter. Including the dark matter halo, The gravitational extent of the Milky Way is perhaps 1 million light-years. Let's be generous and use 1 million. 1 million light-years as the Milky Way's full extent. The observable universe is approximately 93 billion light-years in diameter. 93 billion light-years. The ratio of the observable universe's diameter to the Milky Way's full gravitational extent is therefore approximately 93,000. The observable universe is roughly 93,000 times wider than the Milky Way. In 3 dimensions, volume, the ratio is 93,000 cubed, which is approximately 8 times 10 to the 14th power. 800 trillion times larger in volume. But that is just the observable universe. If inflation is correct, and the full universe is 10 to the power of 23 times larger than the observable sphere, then the full universe is roughly 10 to the power of 28 times wider than the Milky Way, and 10 to the power of 84 times larger in volume. 10 with 84 zeros after it. Let's build some analogies to feel these numbers, the same way we built analogies at the start. If the Milky Way, full dark matter halo, 1 million light-years across, were shrunk to the size of a single grain of sand, 1 millimeter in diameter, then the observable universe at the same scale would be a sphere roughly 93 meters in diameter, the size of a large building. Every galaxy in the observable universe, all 2 trillion of them, would fit inside a sphere you could walk around in 2 minutes, with each galaxy the size of something far too small to see with the naked eye. And the full inflationary universe, at the grain of sand Milky Way scale, a sphere roughly 10 to the power of 22 meters across. For context, 10 to the power of 22 meters is about 1 billion light-years. On the scale where the Milky Way is a grain of sand, the full universe is 1 billion light-years across. That last number breaks the analogy. It is the universe compared to itself. The comparison has outrun the language. Let's try a different approach, thinking about the number of Milky Ways that fit in the observable universe. If you tiled the observable universe with Milky Way-sized galaxies, packed them edge to edge in 3 dimensions, ignoring the voids and the filaments, treating the universe as uniformly dense, you could fit approximately 8 times 10 to the power of 14 Milky Ways inside the observable volume. 800 trillion. That is roughly 100,000 times the number of stars in the Milky Way. More Milky Way-sized boxes than there are stars in our galaxy. And since the observable universe contains about 2 trillion galaxies, and the average galaxy is substantially smaller than the Milky Way, the actual galaxy count is consistent with this packing estimate. There is about 1 galaxy per few Milky Way-sized volume elements, averaging over the whole observable universe. Now think about what this means for life and intelligence. If the conditions that produced life on Earth are not unique, if planets with liquid water and complex chemistry form routinely around the right kinds of stars, and if the observable universe contains roughly 4 times 10 to the power of 23 stars, then even if only 1 in 1 trillion star systems hosts life, that is, still 400 billion living worlds in the observable universe alone. 400 billion. Not in the full universe, just the observable part. And the full universe, on inflationary estimates, is 10 to the power of 23 times larger than the observable sphere. The number of potentially inhabited worlds in the full universe, even on the most conservative assumptions about the frequency of life, is a number that ceases to be meaningful as a count and can only be understood as a statement about inevitability. Life, if it arises at all, does not arise once. It arises everywhere the conditions permit. And the conditions permit in a universe this large, in numbers that dwarf human comprehension. The Milky Way is not alone. It cannot be. Not in a universe this vast. Let's be even more specific about what the numbers imply, because the specificity is important. The Drake equation, the formula proposed by astronomer Frank Drake in 1961 to estimate the number of communicating civilizations in the Milky Way, has 7 factors, most of which remain deeply uncertain. Estimates of the equation's final output range from less than 1, the pessimistic view that we are alone in the galaxy, to millions, the optimistic view that the galaxy teems with intelligence. But the Drake equation was designed for the Milky Way. In the observable universe, 2 trillion galaxies, most of them with their own hundreds of billions of star systems, even the most aggressively pessimistic Drake estimate produces a staggering number when scaled up. If the probability of life arising around a given star is 1 in a trillion, then in a galaxy of 200 billion stars, you expect 0.0002 inhabited worlds per galaxy. That seems vanishingly small. But multiply it by 2 trillion galaxies, and you get 400 million inhabited worlds in the observable universe. At a probability of life, most astrobiologists would consider extremely conservative. The silence of the radio sky, the fact that we have not detected signals from extraterrestrial civilizations despite decades of listening, is not inconsistent with a universe this full of potential life. The distances are vast. Signals disperse as the square of the distance. A civilization broadcasting at the same power as our strongest transmissions would be undetectable by our current equipment at the distance of even the nearest stars. And the universe is young enough, relative to the timescales over which civilizations might persist and broadcast, that we may simply not have listened long enough, at enough frequencies, with enough sensitivity. The scale of the universe does not answer the question of whether we are alone, but it reframes it. The question becomes not, is there life out there? In a universe this large, the size alone argues compellingly for a yes, if life can arise at all. The question becomes, where is it, and why haven't we heard anything yet? That is the Fermi paradox in its purest form. And the very scale that makes the question so urgent also provides some of its most natural answers. Distances so vast that no signal has yet crossed them. Ages of the universe where other civilizations may have flickered into existence and gone dark before we developed ears to hear them. A cosmos enormous enough to be full of life and silent to us at the same time. Chapter 10: The Multiverse. When the universe isn't enough, we have reached the edge of the observable universe. We have speculated about the full universe, probably much larger than the observable sphere. But there is a further conceptual step that some physicists consider seriously, and which the scale of what we have been discussing makes newly urgent. What if there are multiple universes? This is not a fringe idea confined to science fiction. It emerges naturally from some of the best supported theories in modern physics, and the arguments for it, while not amounting to proof, are taken seriously by a significant fraction of working cosmologists and particle physicists. There are several distinct versions of the multiverse concept, and they arise from entirely different theoretical frameworks. It is worth distinguishing them. The Level 1 multiverse, the infinite universe. If the universe is spatially infinite, if it extends without limit beyond the observable sphere, then it contains, by definition, infinitely many regions of space. Given the finite number of possible quantum states in any given volume of space, and the infinite volume of the full universe, every possible configuration of matter must eventually repeat. Somewhere beyond the horizon of our observable universe, there is a region of space statistically identical to ours. There are regions where Earth formed, but no life appeared. Regions where life appeared, but no intelligence. Regions where intelligence appeared, but no civilization. Regions where civilizations arose and collapsed before reaching this question. This is not metaphysics. It is a mathematical consequence of an infinite universe with a finite number of possible local configurations. Given an infinite number of attempts, every outcome happens infinitely many times. The nearest exact copy of our observable universe, if the universe is infinite and uniform, is estimated to be at a distance of approximately 10 to the power of 10 to the power of 118 meters, a number so large that writing it out would require more digits than there are atoms in the observable universe. But in an infinite universe, distance is not a barrier to existence, only to interaction. That copy is out there, in the straightforward mathematical sense, if the universe is infinite. The Level 2 multiverse, eternal inflation. Inflationary cosmology does not just predict a universe much larger than our observable sphere. In its most natural implementation, called eternal inflation, it predicts that inflation never truly ends globally. Different regions of the inflating universe bubble off into separate universes as local. Regions of the inflating field decay to lower energy states, nucleating bubble universes that expand and cool and form stars and galaxies. Our observable universe is one such bubble. Other bubbles are forming and expanding elsewhere in the eternally inflating background. Other universes, with potentially different values of fundamental physical constants, different particle species, different amounts of dark energy, different physical laws. In eternal inflation, the multiverse is not a collection of similar universes. It is a collection of universes that may be profoundly different from each other. Some may have too much dark energy to form structure. Some may have too little dark energy and collapse before galaxies form. Some may have different values of the proton to electron mass ratio, the fine structure constant, the cosmological constant, and be therefore sterile, unable to support atoms, or stars, or chemistry, or life. The anthropic implication is stark. We observe the values of physical constants that we do, the specific value of the cosmological constant, the specific value of the fine structure constant, not because these are the only values possible, but because the bubble universes with other values are either uninhabitable or contain no observers capable of asking the question. We find ourselves in a life-permitting universe because we can only be in a life-permitting universe, in a multiverse containing all possible values of the physical constants. Life-permitting universes are a small fraction of the whole, and every one of them contains observers wondering why the constants are what they are. This is the anthropic principle in its most powerful form, and it divides physicists sharply. Some find it a compelling and perhaps inevitable consequence of inflation, the only explanation for why our universe has the specific, seemingly fine-tuned physical constants it has without requiring a designer. If the cosmological constant were larger by a factor of 100, the universe would have expanded too fast for galaxies to form. If the strong nuclear force were slightly weaker, atomic nuclei would not be stable. If the electromagnetic force were slightly different, chemistry as we know it would not exist. These constants appear tuned, and in a multiverse framework, the tuning is explained. We observe a life-permitting set of constants because we exist, and we exist because our bubble happened to nucleate with this set. Critics argue that the anthropic principle, while logically valid, is scientifically empty, that it explains nothing because it predicts nothing we could test. A theory that says the constants are what they are because we're here to measure them makes no predictions about which constants to expect, and cannot be falsified. The debate between explanatory elegance and empirical testability is one of the deepest methodological tensions in modern fundamental physics, and it centers precisely on the Level 2 multiverse, the Level 3 multiverse, the many worlds interpretation. The third form of the multiverse arises from quantum mechanics, not cosmology. It is in some ways the most radical and in some ways the most mathematically minimal of the three because it requires no new physics, only a different interpretation of the physics we already have. In the Copenhagen interpretation of quantum mechanics, the wave function of a quantum system collapses to a definite outcome when measured, with the probability of each outcome given by the Born rule. In the Everett many worlds interpretation, the wave function never collapses. Every quantum measurement results in a branching of the universe into multiple branches, each corresponding to a different outcome. The electron that is measured as spin-up in our branch is simultaneously spin-down in another branch, equally real, equally physical. The many worlds interpretation predicts a vast, continuously branching structure of parallel universes differing from each other at the quantum level, some by a single photon's polarization state, others by the aggregated quantum differences of billions of years of branching. Every quantum event creates new branches. The total number of branches is uncountably enormous. This version of the multiverse is not the grand cosmic web of Level 1 or the bubble landscape of Level 2. It is, in a sense, closer than either of them, woven into the quantum structure of every atom in your body, branching at every moment with every quantum interaction. Whether any of these multiverse concepts is correct, and whether correct is even the right word for a concept that may be in principle unverifiable, is genuinely uncertain. The multiverse remains a hypothesis rather than a theory, in the technical sense that it makes no predictions we can test with current technology. Its supporters argue that it is the natural consequence of well-tested physics, extended beyond the observable domain. Its critics argue that an unfalsifiable claim, however natural its derivation, is not science. The debate is real and unresolved. But even without the multiverse, the universe we do observe, the 93 billion light-year observable sphere containing 2 trillion galaxies, is already so large that the concept of scale itself breaks down. The multiverse simply takes that breaking and breaks it again. Each level multiplies the incomprehensibility by another factor of infinity. There is a philosophical position that becomes available, and perhaps unavoidable, once you take the full scale of the universe seriously. The universe is not organized around us. It is not scaled to human comprehension. The numbers do not reduce to things we can picture. The processes are not timed to human lifetimes. The distances are not navigable by any technology we can currently envision. The history is not readable by unaided human senses. And yet, against all of it, against the 93 billion light years of extent, the 13.8 billion years of age, the 2 trillion galaxies, the 95% invisible composition, the accelerating expansion, the probable existence of vastly more beyond what we can see. Against all of it, a species that has existed for a third of a millisecond on the cosmic calendar has managed to measure most of it, has determined the age of the universe to 4 significant figures, has mapped the large-scale structure of the cosmic web across billions of light years, has determined that the universe is 68% dark energy and 27% dark matter, has imaged the black hole at the center of its own galaxy, has detected gravitational waves from black hole mergers a billion light years away. The scale of the universe is, in one reading, a statement of our smallness. In another reading, it is a statement of our reach. Both readings are simultaneously true. That is perhaps the most honest thing that can be said about what the size comparison means. Conclusion: our address in the cosmos. And why it matters. Let's go back to where we started. A number, 100,000, light years across the Milky Way. We have now seen what that number sits within. The Milky Way sits in the local group, a gravitationally bound family of roughly 80 galaxies, spanning 10 million light years. The local group is a minor component of the Virgo supercluster, which is one lobe of Laniakea, which spans 520 million light years. Laniakea is one node in the cosmic web, embedded in the observable universe, 93 billion light years across, containing 2 trillion galaxies, made predominantly of dark matter and dark energy, none of which we fully understand. And the observable universe is probably a tiny fraction of the full universe. And the full universe may be one of infinitely many. The Milky Way, 100,000 light years across, sits within all of that. There is a specific kind of vertigo that this comparison produces, a cognitive vertigo, a sense of the ground, dropping away under your intuitions. The vertigo is real and it is healthy. It is the feeling of your mind trying to hold something larger than it was built to hold, straining against the limits of an intuition evolved for a world of meters and kilometers, hours and days. But there is also something else that this comparison produces if you sit with it long enough. Not diminishment, its opposite. Here is what the scale of the universe actually tells us about the Milky Way, and about us. The Milky Way is 100,000 light years across. It contains 200 to 300 billion stars. It has been forming stars for nearly 13 billion years. It has a supermassive black hole at its center that weighs 4 million solar masses. It is in the process of a slow gravitational merger with the Andromeda Galaxy that will complete over the next 4 billion years. None of that is diminished by the fact that there are 2 trillion other galaxies in the observable universe. In fact, what the scale of the universe does is reframe what the Milky Way represents. In a universe of 2 trillion galaxies, the Milky Way is not special by being unique. It is one representative of a class of object that is, cosmically speaking, extraordinarily common. But the commonness is not the point. The point is what the commonness implies. If the Milky Way is a typical galaxy, and by most measures it is, a fairly large spiral, a fairly ordinary star formation history, a supermassive black hole of no particular distinction. And if the Milky Way produced, on one of its 300 billion planets, a species capable of building telescopes and asking questions about the structure of the universe, then that process, the emergence of curiosity from chemistry, is not a miracle confined to one special galaxy. It is something the universe does. In 2 trillion galaxies, with hundreds of billions of stars each, over 13.8 billion years, the emergence of beings capable of comprehending the universe is not a singular accident. It is, statistically, an expectation. The universe is not vast and empty with a small, flickering point of consciousness here. The universe is vast and structured and full, with the conditions for consciousness distributed across it in ways that, given the numbers, make it almost certain that we are not the only example. We are, if the scale means anything, one of an enormous number of vantage points from which the universe is examining itself. That is a strange and powerful thing to be. Think about what it would mean to be in a galaxy inside one of the great cosmic voids, one of the 100 to 500 million light-year expanses of near emptiness that make up 80% of the universe's volume. A civilization in such a galaxy would look out and see very little beyond their own stars. Their nearest galactic neighbors might be tens of millions of light-years away. The rich tapestry of galaxy clusters, the filaments of the cosmic web, the thousands of galaxies visible in a typical field of view from our position, all of that would be absent. Their cosmology, even if they developed one, might not look much like ours, because the evidence of large-scale cosmic structure would be far harder to read from inside a void. We are fortunate to be where we are. The Milky Way sits in a node of the cosmic web, embedded in the local group, part of Laniakea, with the Virgo cluster pulling gently on us from 53 million light-years away. Our night sky in the direction of Virgo contains hundreds of galaxies within range of a modest telescope. Andromeda is visible to the naked eye from a dark site. The cosmic web is legible from our position within it. We live, cosmologically speaking, in a well-connected neighborhood with a view of the universe's large-scale architecture that is far richer than what a void-dwelling civilization would have. The size of the universe is not just a fact about distance, it is a fact about access. And we have, from our particular address in the cosmos, unusually good access to the evidence. The other thing the scale comparison reveals is how recent our understanding of it is. For most of human history, for the entirety of the period that the cosmic calendar places in the last 10 seconds of December 31st, the observable universe was smaller than the solar system. The stars were lights on a celestial sphere. The scale of the Milky Way was not understood until Harlow Shapley measured the distances to globular clusters in the 1910s. The existence of other galaxies was not confirmed until Edwin Hubble measured the distance to Andromeda in 1924. The expansion of the universe was not discovered until Hubble's analysis of galaxy redshifts in 1929. The acceleration of expansion, dark energy, was not discovered until 1998. The revision of the galaxy count from 200 billion to 2 trillion happened in 2016. The first image of Sagittarius A star, our own galactic black hole, was published in 2022. The full picture of what we have covered in this video: the Milky Way embedded in the local group, embedded in Laniakea, embedded in the observable universe, with dark matter and dark energy dominating the energy budget, with the full universe probably vastly larger than what we can see, has been assembled in its complete form within a human lifetime. Most of it within the last 100 years, a significant fraction within the last 25. Consider what that timeline actually means. Every person alive today, older than about 60, was born into a world that did not yet know the expansion of the universe was accelerating. Every person older than about 100 was born into a world that did not yet know other galaxies existed at all. That thought the Milky Way was the universe. The entire intellectual architecture of modern cosmology, the Big Bang, inflation, dark matter, dark energy, the cosmic web, the 2 trillion galaxy count, the age of 13.8 billion years, is younger than living memory. This is a staggering pace of discovery. In the span of a single human lifetime, our picture of the cosmos has expanded from 1 galaxy to 2 trillion, from a static universe to an accelerating expansion, from no knowledge of dark matter to its domination of the mass budget, from no understanding of the universe's birth to a detailed model of its first fractions of a second. The James Webb Space Telescope, launched in 2021, is currently showing us galaxies from the first few 100 million years of cosmic history, structures that are already challenging our models of early galaxy formation, appearing larger and more mature than our best theories predicted. The picture is not complete. It is being revised in real time with every new deep field image and every new spectrum. That is the other thing the scale teaches. Not just how large the universe is, but how recently we found out, how new this knowledge is, how much remains unknown. The Hubble tension is unresolved. Dark matter has not been directly detected. Dark energy is unexplained. The topology and true extent of the full universe are unknown. Whether the multiverse exists is unknown. Whether we are alone in this vast structure is unknown. The universe is not a completed picture. It is a picture being drawn in real time by the instruments we have built and the minds we have trained and the questions we have learned to ask. There is a photograph that was taken in 1990 by the Voyager 1 spacecraft, which we mentioned at the beginning of this video, crawling away from us at 17 kilometers per second. At the request of the astronomer Carl Sagan, the spacecraft's camera was turned back toward the inner solar system from a distance of about 6 billion kilometers. Earth appears in the photograph as a tiny point of light, less than a pixel wide, suspended in a ray of scattered sunlight. Sagan called it the pale blue dot. He said, "That's here, that's home, that's us. On it, everyone you ever heard of, every human being who ever lived out their lives. The aggregate of all our joys and sufferings, thousands of confident religions, ideologies and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilizations, every king and peasant, every young couple in love, every hopeful child, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. That was from a distance of 6 billion kilometers. One photograph of one planet in one solar system, in one spiral arm of one galaxy, in one cluster, in one supercluster, in one small corner of the observable universe. Now take that photograph and extend the zoom. Pull back from 6 billion kilometers to 26,000 light years, the distance from the sun to the galactic center. Pull back to 100,000 light years, the full stellar disk. Pull back to 1,000,000 light years, the outer edge of the dark matter halo. Pull back to 2.5 million light years, far enough to see Andromeda as a separate galaxy, our gravitational partner in the night. Pull back to 10 million light years, the full local group in a single frame, 80 galaxies scattered across a volume. Voyager 1 would take longer than the current age of the universe to cross. Keep pulling back. 50 million light years. The Virgo cluster fills the frame, thousands of galaxies in a dense, tangled knot. 500 million light years. Laniakea, the full sweep of our supercluster complex, a gauzy web of filaments and nodes. 5 billion light years. The cosmic web becomes visible in full, the filaments and voids forming a pattern that looks strikingly like the neural network of a brain. Not because the universe is conscious, but because gravity and the physics of structure formation, working over billions of years, produce branching, filamentary geometries at every scale where those forces dominate. 93 billion light years, the observable universe, a sphere. Inside it, 2 trillion galaxies. And at the center, not because we are special, but because every observable universe is centered on its observer. One small spiral galaxy, one middle-aged star, one rocky planet, one species, one moment of looking outward and asking, how big is all of this compared to where we are? The Milky Way is 100,000 light years across. It contains 300 billion stars. It is, compared to the observable universe, a grain of sand on a beach. It is compared to the full universe on inflationary estimates, incomprehensibly smaller still. And in it, on one arm of one spiral, around one middle-aged yellow star, on one rocky planet at the right distance from that star to have liquid water on its surface, over the course of about 4 billion years of chemistry and evolution, and contingency and luck, something arose that could look outward, build instruments, measure the acoustic oscillations of the early universe, map the cosmic web, infer the existence of dark matter and dark energy, estimate the number of galaxies, and ask how big the universe is compared to the galaxy it lives in. The universe is roughly 1,000,000 times wider than the Milky Way. In volume, 1 billion times larger at minimum. Possibly 10 to the power of 23 times larger than that. Possibly infinite. And in it, in this one galaxy, on this one planet, in the last 10 seconds of the cosmic calendar, something became aware of all of it. The universe is roughly 1,000,000 times wider than the Milky Way when you measure stellar disk to observable sphere. 1 billion times larger in volume. possibly 10 to the 23 times larger than that in the full post-inflationary space, possibly infinite. The ratio keeps growing with every layer of the onion you peel back, and each new layer is not a refinement of the previous number, but a qualitatively different order of magnitude, a new tier of incomprehensibility. And the Milky Way sits inside all of it. One galaxy, one spiral arm, one star, one planet, one question. How big is the universe compared to our galaxy? The honest answer is incomparably bigger. So much bigger that no analogy fully works, no number fully registers, no scale model fits inside any imaginable space. The universe is bigger than our ability to comprehend it. Not because our ability is small, but because the universe is that large. But the question was never really about a number. The question was about what the number means. And what it means is this: we are small, and the universe is vast, and we are the part of it that knows.